I welcome you all to the Spark Research YouTube channel. This is Dr. Virchan, Assistant Professor in the Department of EC, and in this session we are going to take some more questions from the GATE 2024, particularly which belongs to the Unit 3 and 4. So this is another session of Analog and Digital Communication series. So let's take the question. Here is the overview of the GATE. So mostly GATE may ask the questions from the digital communication also. So let's take the question. See, in this session, we are going to take the more questions, so we will try to go a little bit faster, right? So the question is the full scale sinusoidal signal is applied to the 10 bits. It's given the fundamental signal component in ADC output has a normalized power of 1 watt. So 1 watt is given for signal component power, and the 10 bit ADC. So these things are given, and the total noise and the distortion normalized power is also given, that is noise power. So the effective noise number of bits, right? So in order to the effective number of the bits, this is asking. So let me tell you how to solve. Like first of all, your answer should be the B, right? So that is the the number of bits should be 8. So here, how can we solve the question? So first of all, we know the SNR, that is this formula. If you remember, then you can find out very easily. So here SNR, we can use this 6.02 n plus 1.76 dB. So we can calculate the SNR from the parameters given here, and then we'll equivalently we'll check. Then after the putting the values of SNR here, we can find out the value of n, right? So this is the technique to solve. Here is the SNR background. What is the SNR? We have already discussed. If you wanted to check, you can go through the another previous video. I will drop in the link. So SNR, you can calculate it using this equation. So let's come. So signal power is given 1 watt, and the noise pulse distortion power, that is also given 10 to the power minus 5, that is 10 microwatt. So SNR, we can directly calculate the ratio of the the message power divided by the noise power. If you will convert into the log, you will get the 50 log. Now since you got this, so directly you can put it into this formula, right? So after getting this, so just put it into the formula, like instead of the SNR. So once you will put it, and then you will get the noise ratio, the number of bits, right? That will be almost equal to 8. So this is the final answer. Okay, so here is the shortcut solutions. Here first get the solution, the first find out the SNR value from the particular, the whatever it is given in the question. So signal power is given 1 watt, noise power is given 10 microfarad. So get the SNR, and you can convert into the dB scale, and then after converting into the dB scale, you can put the put the values in this SNR formula, and you can get the number of bits that will be equal to the 8. Here is another question. So xt is equal to given via random process where amplitude A and phase is also given independent of each other, uniformly distributed into the interval -2 to 2 and 0 to twice by respectively. And xt is like it is already given 8-bit uniform mid-rise type quantizer. Mid-rise type of the quantizer we are using. So this is normal mid-rise PCM type of the quantizer only, right? Given that the autocorrelation is given like xt is equal to this rxt is equal to twice by 3 cos omega naught t, and the signal to quantization ratio is like the question is asking. So very simple, right? We have already discussed about the background, you can check it. So let's solve here. So p of x is given, that is twice by 3, already it is given in the question. So that is the signal power only. So we have to find out the noise power. So how we'll find out the noise power? So first get the del is your the quantization gap. So how will you find out? So total the input range, how much, that is 4, and divided by how many bits we are using. We are using the 8 bits, so 2 to the power 8. So that is the total length, that is L. So total range, that is 4. And so this is something like that. Let me tell you, like this is the total range, right? So from here to here, this is the total range. So that is equal to 4, and 256 is that in how many paths you are dividing. So you are dividing into the 8 bits, means a total 2456. So what will be the size of this one small del? So that is equal to your step size. So that will be 1 by 64. And so you have to calculate the quantization noise. So that will be equal to the del square by 12, and then 3, that formula you can check it the previously, 3 by 2 L square. So now once you will put all these values, you will get the noise power, this one, and then calculate the value of SNR, that is the P, this one already given here. So you can copy paste the data here from here and here, and then you will get the SNR value. Further you have to calculate into the dB scale. So just take the 10 log, and base of that you will get the SNR value. So this is the final answer, right? Let's take the another question. So same questions you can solve here. Px is from the autocorrelation functions you can get the the signal power, that is 2 by 3 watt, and then the noise power you have to calculate. So how will you calculate? So noise is nothing, del square by 12. So del square you can first calculate, that is the step size divided by the total L, and then further you can get the value of the noise power using this equation. So this will be value, and further convert it into the dB scale, that is SNR value. You will get here the total the signal to noise ratio in the dB scale, right? Okay, so let's take the another question. Here is the another question. Source transmit a symbol as taken from -4, 0, 4 with equal probability over an additive wide Gaussian noise channel. The received noisy symbol R is given by R is equal to this one, with the noise W is 0 mean and variance is 4 as independent of S. So using this at optimum symbol, what will be the optimum symbol error probability rate? Right. So since we are sending the three datas, -4, suppose this is your -4, P of R by S is equal to -4, and this is P by R by S is equal to +4, and of course 0 also we are sending. So here if you'll see now, there is a region where we'll have the interference in this region, and also in this region, means what? Means in this region what will happen, whenever we are sending 0 we may detect the -4, we are sending the the 4, we can detect the 0. So we have to find that probability of error, that is what will be the optimum symbol probability of error there will be, right? Okay, so let's see the solutions, how to find out. Okay, so these questions already given here. So here you can check the decision boundary. So whenever you are checking the decision boundary at R is equal to -2 and R is equal to +2, both you can find out, right? So here we will since already it is given the variance, so that is square root of 4. You can calculate the 2, that is distance from the signal to point boundary. Already we have got this value. So case 1 here, case 1 for this case, like here we can calculate the probability of error, that is P is greater than W. For this case, that is Q is equal to 1, and if it is P of error when S equal to 0, in this case P less than minus up to and plus of P greater than W greater than 2. So in that case 2 into Q1, and both will be equal, that is why we are getting, and then S is equal to 4, and then it will be P W less than -2, that will be equal to 4, right? So we'll add all those 4. So 1 2 3 4, right? So 2 here, 2 here will add, then we'll get the total. Okay, so let's see the more detailed calculations here. So here optimum decision rule, since the symbols are equally likely and the noise is Gaussian, right, already given in the question. So in between -4 and 0 there is a -2. So in between 0 to 4 it is +2. So we have the three different reason to decide what are that. So decide -4 whether so R is less than -2, and if you wanted to decide 0, means if it is your R is in between -2 to 2, then in that case your value will be 0, and similarly 4, it will be only for R greater than 2. So whenever you are transmitting -4, R should be greater than minus of 2. So in that case probability of error of -4 will be Q of 2 by 2, so that is equal to Q of 1. And similarly if for second case the are in between minus 2 and 2, so that will be the 2 of q and 2 by 2, again 2 of q1. Similarly for less than 2 also it will be q of 1, so total it will be 1 by 3 average probability, average symbol error probability, that is equal to 1 by 3, and the first region, second and third, right, both. So this will be 4 by 3 q1, so the final answer is 4 by 3 q1. Okay. Okay, so let's take one more question here. So digital communication system transmits through a noiseless band limited channel, that is minus W to W. The received signal ZT at output receiving filter is given, right? Filter already given. Bn is a symbol and action is the overall system noises response to the signal symbol. So receives a signal has sampled at this t is equal to empty. The Fourier transform of xt is xtf, also Nyquist condition, right? Which should satisfy in order to avoid this ISI inter-symbol interference. So question is that what is the inter-symbol interference? So whenever you are transmitting the data 1 and data 0, there will be the interference in between, the while you are sending 1 and 0. So that is ISI only. So you have to find out the Nyquist criteria, so that you can have the 0 ISI. So option your the mark to all means any option is correct. So x of f plus m by t is equal to t, so we have to find this condition. So let's see the solutions here. So I just got this screenshot from your Bipilathi book, fourth edition. You can check it. So here is the Nyquist first criteria for zero symbol, zero ISI, that is inter-symbol interference. So in order to satisfy this condition, whenever you are, the pulse satisfying the criteria, pulse zero ISI, all remaining pulse centers or signaling in instant and shown in figure where so several successive pulses centered at this, right? So here, like, start from the 0 SI time domain x of nt, that will be equal to the 1 and 0. Here x of nt is given, and for further if we will move from time to frequency domain, then in the time domain you are sampling at this rate, and then convert in the frequency domain, that will be x of the f of m by t, and further take the Fourier transform like del of t, that is the dt of the discrete time Fourier transform. So this will be equal to 1. So equate both sides, you will get this condition. So now here all options are correct only. Okay, so digital communication system. Okay, so same questions only. If whenever you are transmitting with respect to the some sampling theorem and pulse trend, right? Then you have to convert into the time to frequency domain. So major problem is that whenever you are sampling at every sample, that is x of mt. So according to the Nyquist sampling rate theorem, sampling time results in the periodic replication in the frequency, that is the major advantage here. So now you have to find out the sampling frequency because you are converting into the time to frequency domain. So once you will convert, then you need the some filter in order to avoid the higher higher frequency, right? So that we can detect the masses properly, and so that is why the criteria is there, so that will satisfy this condition. Okay, one last question. Let's go fast. We'll conclude. So this is the concluding question. So continuous time signal xt is given. This is sampled at the rate of the 15 hertz, and the sampling sampled signal x is whenever it will pass through the LTI system, and ht is given. So producing x dot c. So what will be the x naught t? So what will be the output? So that is the question here. So xt is given and f naught is also given and fs is given, right? So these things are given. So f is equal to how much? Plus minus 4 and plus of k of 50, right? So because f of s is given, so you have to find. So sampling frequency, if will the multiply in a sampling frequency, it will ultimately multiply in the frequency. So it will result into the plus minus 4 and 15 plus then plus minus 11 and then plus minus 18, right? So if we'll keep on adding plus minus, you will get h of t. This is your filter that we are using. So this is the sync function. So like low pass filter with cutoff of 1 hertz, and your message signal is nothing. This is your sine of 35. You can convert it into the cos to sinusoidal signal, and then it will be shifted to the plus minus, right. It will lies in this range. So since we are using this filter now, so frequency must lie so in this range. So of course the your frequency from here now, it will pass the only your filter will, this filter will pass the both, this filter will pass this only 19, right. That is 15 plus 4 only. So and fs, so amplitude you can also calculate, that is to this one, and then phase shift you can also calculate from here, and you will get the final answer. So that will be this, right. So frequency you got, the amplitude you got from here, and then you got the phase. So that's all in this session. So play today, stay healthy tomorrow, and learn for a lifetime.